When we imagine first contact with an alien civilization, we often picture spaceships, translators, and a lot of awkward glances. But beneath this science fiction gloss, there lies a very old assumption, almost a superstition, that if everything else fails, mathematics and physical constants will save the conversation. We both measure light speed the same. 2 and 2 is 4, regardless if the calculator has 2 eyes or 4. The vocabulary of numbers and shapes, the rhythm of prime sequences, the elegance of geometry, surely we think these are universal. A hydrogen atom on Earth sings the same special notes as one in the Andromeda Galaxy, and gravity pulls the same way no matter who is watching. So it feels only natural to believe that mathematics must be stamped onto the universe itself, a cosmic language waiting for us to speak with alien minds. Yet even this comforting notion contains a quiet trap. We assume mathematics is universal because it seems so fundamental and necessary to us. But what we call mathematics is not the universe's raw code. It is the set of tools and symbols humans developed to talk about that code. If alien minds evolved under different skies, with different senses, bodies, and intuitions, then the mathematics they invent to describe their reality may be as alien to us as their language or their biology. Our first contact may not be with ships or signals, but with a piece of mathematics we cannot recognize as mathematics at all. Today we'll explore how and why that might happen. We will begin with why we believe mathematics must be universal, then examine how astonishingly non-universal it is, even within our own species, and from there we'll consider what mathematics might look like to other minds, creatures of gas and ocean, hive intelligence and magnetic sense, and whether we could ever bridge those differences when the moment of contact finally comes. And if all that sounds fun, grab a drink and a snack, maybe in an official SFA coffee mug, and let's dive into the strange and beautiful possibilities of alien mathematics. Mathematics has earned its reputation as the backbone of science. We describe falling apples and orbiting planets with the same equations. The speed of light, the structure of atoms, the geometry of space-time, these seem entirely independent of culture or species. If physics is universal and mathematics is the language of physics, then surely mathematics must be the Rosetta Stone of the cosmos. This idea is not merely a philosophical hunch, it has shaped decades of SETI research. When we imagine detecting an alien signal, we expect to find sequences of prime numbers or geometric arrangements that cannot be natural phenomena. The famous Arecibo message broadcast in 1974 was built on exactly this assumption, that any intelligent species would recognize prime numbers, picture elements shaped into a grid, and encoded patterns representing atomic numbers. Mathematics feels like the one domain where intelligence and nature overlap absolutely. Even in fiction, aliens often use math as a calling card. In Contact, Carl Sagan's aliens use prime numbers to announce themselves. In other stories, extraterrestrials demonstrate the Pythagorean theorem or send fractal images. Across decades of storytelling, math has served as a symbol of common ground, a promise that intelligence everywhere must converge on the same truths. This belief is reassuring not only because it offers a way to talk to aliens, but because it suggests our discoveries are not parochial. If aliens independently discovered calculus or quantum mechanics, or the laws of relativity, then our mathematics is not merely a human invention, but a glimpse into the universe's own architecture. But the sense of universality deserves scrutiny. First, it does assume an objective reality, which is sort of required given for science but is unproven. There really is no sane way to prove or disprove that, and thus reality could be subjective and our group minds pushing at it have forced it to a certain local pattern, on which it doesn't match what aliens would perceive. This seems crazy, but so does debating if 2 and 2 always makes 4, and when you get down to it, the fundamental mismatch we call the Fermi paradox, that all general science and intuition tell us this huge and ancient universe ought to be flooded with life, but we see no sign of it, seems fundamentally at odds with what we know of science. So, paradoxical or impossible thoughts, while it might irritate Sherlock Holmes to say so, cannot simply be ruled out. We also should not be assuming potential contact with aliens is only common from our own universe. There may be all sorts of wonderfully non-Euclidean realities, or ones where physical constants are different. Indeed, the latter at least is pretty much an inevitable consequence of string theory, should it turn out to be right. Also, it might be a lot easier to step from some alternate reality, just one atom width away in a fifth dimension, than to send signals or ships trillions of miles. But beyond that, when we say mathematics is universal, what we really mean is that the physical patterns we use mathematics to describe are universal. A triangle in the small Magellanic Cloud still has 3 sides, and of course its interior angles still add up to 180 degrees, unless it's laid out on a curve like a spherical globe or a saddle-shaped potato chip. Still, a harmonic oscillator behaves the same whether built by humans or aliens, presumably. But the mathematical framework we impose on these phenomena, the symbols, structures, logic, and assumptions we use, is a human creation, shaped by human cognition and human culture. Consider how deeply we tie concepts like number, shape, and proof to our own sensory experience. We grew up in a world of discrete objects, apples, stones, planets. Counting feels obvious because we evolved in an environment that presents things as separate entities. Geometry feels natural because we live in three-dimensional space with solid surfaces and straight lines. And our logic, built on statements being true or false, comes from a worldview in which contradictions are often dangerous. These intuitions are not guaranteed to appear in other minds. Mathematics may be universal in principle, but the pathway by which minds reach it could vary wildly. The truths may be shared, but the routes to those truths may differ beyond recognition. Before we examine alien possibilities, it's worth looking at the enormous variation within our own species. Humanity is a single biological species on a single planet, sharing broadly the same sensory organs and evolutionary pressures. Yet even among humans, mathematics has never been a single unified tradition. If humans struggle to agree on what counts as mathematics, why should we believe aliens will converge on the same system that we use? Math is not the same, even for humans. Human history is rich with mathematical diversity. Some cultures built elaborate number systems and geometric models. Others barely counted at all. Some embraced abstract symbols. Others used tangible tokens or knots or string. The assumption that mathematics is a single universal thing evaporates as soon as you examine how humans have approached it across time. Consider how long it took humanity to invent zero. The idea of a placeholder and then a true number meaning nothing emerged only after millennia of arithmetic. Without zero, performing large calculations is cumbersome, and negative numbers are nearly impossible to express. Imaginary numbers, central to modern engineering, were dismissed as nonsense for centuries. Calculus, the language of motion and change, had to wait until Newton and Leibniz. Probability theory took even longer because the idea that randomness has structure was philosophically unnerving. Even more startling is the variation in how humans approach counting itself. Some cultures did not rely on fixed numerals at all. The Paraha people of the Amazon famously only used words that mean things like a small amount and a larger amount, with no exact number terms the way we think of them. This wasn't because they lacked intelligence, but because their daily lives simply didn't require the abstraction of large numbers. Counting, which feels so obvious to modern humans, was a skill literally invented and refined over tens of thousands of years. Writing numbers down is just another revolution. Roman numerals are elegant but unwieldy for calculations. Try multiplying using them, and you'll quickly appreciate why mathematics never reached its full potential in that system. Possibly the greatest engineers of antiquity limited in their advancement by their own math. When positional notation spread, mathematics leapt forward, not because the universe changed, but because humans found a better way to describe it. Even logic, the foundation of proof, has not been consistent among humans. Classical logic insists a statement is either true or false, with no wiggle room. But mathematicians eventually invented alternative logical systems. Fuzzy logic allows statements to be partly true and partly false at the same time, which is how everyday things actually behave. A room can be somewhat warm rather than simply warm or cold. And one side of it might be warmer than the other, as might the temperature vary with the time of day. Probabilistic logic treats truth in terms of likelihoods instead of absolutes, letting you reason with uncertainty the way weather forecasts or medical diagnoses must. Pair-consistent logic does something stranger. It allows contradictions to exist inside a system without blowing the whole structure up, which is useful for situations where information is incomplete, conflicting, or arise from multiple unreliable sources. Some have suggested this would be a better approach to handling wave-particle duality and other quantum behavioral issues. So these are not science fiction curiosities. They are real tools used in computing, engineering, and philosophy to handle the messy, uncertain world we actually live in. Needless to say, if your logic determines what counts as a valid proof and your culture determines what counts as a useful number, then mathematics is not purely discovered. It is also invented. A human, a Greek philosopher, a medieval merchant, a Mayan astronomer, and a modern physicist may all talk about mathematics. They're not talking about the same mathematics. And yet all these examples stem from a single species, with the same senses and broadly similar brains, raised on the same planet. Alien minds, shaped by entirely different bodies and worlds, could diverge from us far more dramatically. If humans can barely agree on what a number is, imagine a species that does not perceive objects at all. If humans disagree on what counts as valid proof, imagine a species that reasons musically or spatially or chemically. Human diversity in mathematics teaches us a crucial lesson. Mathematics is not inevitable. It is not forced upon us by nature. It is something we grow into, slowly, painfully, through cultural refinement. And the alien species will have undergone their own refinement, guided by their senses, their survival needs, and their modes of thought. The mathematics they arrive at may share some universal truths, but structure and expression may be entirely unrecognizable to us. If the first message we receive from the stars is a mathematical one, we should be prepared for the possibility that we won't immediately know what part of it is the math. How alien biology could reshape their mathematics. If mathematics varies among humans, it may diverge vastly more among alien species whose bodies, senses, and environments bear no resemblance to our own. A brain is not a neutral fact-finding engine. It is a survival tool, honed by evolution to solve problems that matter to the organism. That is why we are actually bad at it. We can usually catch a ball, which requires huge amounts of brain power, before we do basic arithmetic, and even then, rarely as well as even the crudest calculating machines. Our mathematics reflects our world, a place with discrete objects, firm boundaries, repeating cycles, and geometry of surfaces and solids. Aliens would inhabit realities that might not offer those cues, or might offer others we barely understand, and their minds would reflect that. Picture a civilization that evolves in the deep layers of a gas giant. Their surroundings would be an ocean of drifting vortices, endless gradients, and merging currents. They might never see a sharply defined object in their lives, possibly including themselves, even assuming they have mirrors or eye stalks to look at themselves. Counting assumes separateness, but to them, things constantly blend. In such a world, mathematics might begin with flows and fields, not with integers or shapes. They may treat the world as a continuous tapestry, where distinctions are fluid and the concept of two is less meaningful than the concept of more dense here, less dense there. Thicker air, thinner air. Their earliest mathematics might resemble fluid dynamics or wave mechanics, long before anything we would call arithmetic. And the boundaries of identity are fairly ambiguous and arbitrary. Where do you begin and end? I don't even mean an existential sense of how we change with time, or if you're still just as much you if you lose a limb. Where is the edge of you? Do you include your dead skin cells? The top layer of your skin maybe, but not the ones that fell off. Does it have to be contained inside you? What about all those vital microorganisms inside you that share no DNA with you, from your gut bacteria to your mitochondria? When exactly did DNA become the keystone of identity anyway? We've only even known it existed for less than a century. We are what we eat, and probably also what we use to digest that food. Now imagine beings that evolved as cooperative swarms, like ants or bees, but with individual minds combining into collective intelligence. For them, individuality might be a transient or negligible feature. Do not assume the hive mind simply happens to be an individual. The swarm might expand or contract smoothly, with no clear boundary for counting. Their mathematics could begin with densities, connectivity, or probabilistic motion rather than discrete enumeration. Where a human sees 30 ants, a swarm might see only the pattern we are making right now. Their core intuitions would align with networks, not numbers. Ironically, for us, the real world, seemingly infinitely divisible, was counterintuitive, till we found discrete states down the otherwise very counterintuitive quantum scale. For them, it might be the way around. Quantum seems insane to them because it does have discrete values. Incidentally, if you're not clear on that, there are numbers between 1 and 2. You can have 1.5. It means something. The letters A, B, and C are in arbitrary order, and there's no such thing as 2/3 of an A plus 1/2 B. Our numbers are not. They can be divided infinitely. Let us instead consider a species living beneath the ice of a frozen ocean, surviving entirely through sound. Vision shapes much of human mathematics. We draw graphs, diagrams, and geometric proofs. But a species that sees through sonar might think acoustically. Their mathematics could emerge from harmonics, resonances, and interference patterns. A proof might be a tone sequence, a relationship shown by combining notes in a way that resonates physically. For such beings, equations might be sung rather than written, and symmetries might be heard rather than seen. Creatures with an innate sense of electromagnetic or gravitational fields could develop mathematical intuition about vectors and tensors as naturally as humans grasp basic geometry. We consider advanced, multidimensional geometry or field theory might be their arithmetic, and would never occur to them they need to include that in their Rosetta Stone to us, any more than we think we need to include what 1 and 2 were. And I don't mean the symbols for 1 and 2, I mean the very concept of 1 and 2. They might feel the krill of a magnetic field the way we feel the warmth of sunlight and think in higher dimensions without effort. Their mathematics might not even have symbols, but instead treat space itself as a manipulable mental object. Even the experience of time could profoundly shape mathematics. A species with extraordinarily long lifespans might regard infinitesimal rates of change as natural and consider our calculus astonishingly rushed. I often suggest the signal that a species would send to our planet by a laser as opposed to an omnidirectional signal might simply have the number 365 repeating every 24 hours, a way of saying knock knock, we know you're there. We see your planet that spins 365 times per year and this often. But for a very long-lived species that thinks at a glacial pace, they might not even think to include something like that or recognize it if we tried to approach them that way. A species with extremely rapid cognition, on the other hand, might treat recursion and iteration like sensory experiences, effortlessly unwrapping nested relationships that would overwhelm a human mind. All of these differences point to a profound conclusion. Mathematics is not merely shaped by cognition, it is shaped by the environment that produced that cognition. What we find intuitive, numbers, shapes, symbols, emerges from our particular world. Alien realities might emphasize continuity instead of discreteness, patterns instead of boundaries, fields instead of objects, harmonics instead of shapes, or dimensions we barely conceptualize. If alien mathematics begins with unfamiliar printers, their entire structure of knowledge might rest on foundations we do not share. To them, our mathematics might feel like a strange historical artifact, clever but painfully limited, like trying to describe a hurricane using only counting beads. And again, we should not be assuming the aliens simply happen to live elsewhere in this universe. They might be reaching out to us from an alternate reality. Before we assume aliens will understand our equations, we must accept that they may not even understand why we choose these building blocks in the first place. Alien logic, when the rules themselves don't match. If aliens differ from us in biology and environment, it follows naturally that their logic, the set of rules they use to determine truth, might differ as well. And here lies one of the deepest challenges for communication. Two species may observe the same universe and yet disagree on how to reason about it. Humans take classical logic for granted. Every statement is either true or false, and contradictions are mistakes. This seems obvious because it typically works. A predator cannot be both behind you and not behind you, unless it is a giant hive mind or maybe a cosmic megafauna whose mouth you happen to be standing in. A tool cannot be both broken and unbroken. Contradictions in our daily lives are dangerous. Yet humans have already invented many alternative logical systems. As we said earlier, fuzzy logic allows partial truths. Something can be partly true and partly false. Probabilistic logic embraces uncertainty as a feature, not a flaw. Pure-consistent logic treats contradictions as manageable, not catastrophic. Intuitionist logic rejects truths that cannot be demonstrated constructively. The supermajority of humans, now and in the past, had little of any training in classical logic either, yet operated just fine, and that even includes a lot of inventors. I think most people would be better off if they had more training in logic, but that's neither here nor there. And again, these alternative systems are not philosophical curiosities. They solve real engineering and scientific problems. But they emerge from human culture gradually, after millennia spent wrestling with questions classical logic could not elegantly answer. Other species might begin with very different assumptions. Consider a hive mind of species where knowledge emerges collectively. Their idea of proof might not be a chain of symbolic steps, but a pattern of agreement across many minds, where coherence and convergence matter more than linear deduction. A valid argument might be one that achieves stability in the group, not one that satisfies a rigid, axiomatic progression. And while this would seem a barrier to science, we don't know that it is, and we don't know that you need science to get spacefaring technology. We got everything up through the last few centuries mostly without it, and a hive mind has a lot of brain and a lot of metaphorical hands to brute force its way through problems. This divergence in logic potentially affects every part of mathematics. A proof built on classical deduction may be meaningless to a species whose reasoning is emergent or consensus-based. A theorem we consider airtight might look incomplete to a mind that expects truths to be demonstrated through dynamics, patterns, or stability over time, and an alien proof might seem like a shifting geometric or social process than a tidy sequence of statements. Even the notion of axioms, foundational truths accepted without proof, might strike aliens as peculiar. They might raise their eyebrows, all 200 of them, at the statement, "I think, therefore I am." They might expect that all truths must be derived from observed patterns in nature, or they may have no concept of foundational truths at all. Communication becomes challenging when the rules of reasoning are different. And keep in mind, even if their approach is demonstrably wrong or inferior, that does not help us in figuring out how to speak to them to explain why they are wrong. If an alien message encodes complex theorem or conceptual structure, We may not even recognize which parts represent assumptions, which represent operations, and which represent conclusions. A sequence we interpret as random noise might be an elegant argument written in logic we do not share. It is entirely possible that our first confirmed alien signal will be something that we can measure, record, and admire but cannot comprehend. Only after long study might we realize the message was structured according to a logic alien to human minds. And while the underlying truths may be universal, the way those truths are expressed could be so foreign that we miss their meaning entirely. Yet even this does not make communication impossible. It simply means we must be prepared to discover not only alien mathematics but alien logic itself, a framework of thought built on foundations entirely different from our own. If we ever communicate with aliens, mathematics is often treated as the universal language, but that assumes time isn't the real barrier. Once messages take decades or centuries to arrive, meaning starts to drift in ways no equation can fully fix. For a great reminder of how strange time already is, watch my friend Joe Scott's Nebula documentary, Oldest and Newest Places on Earth, where he moves from some of the oldest exposed rock on the planet to lava actively reshaping Hawaii, billions of years of history in a single episode. That same long view perspective carries in this month's Nebula exclusive The Future of Interstellar Communication, which looks how civilizations stay in touch across light years when fast conversations simply are not possible. Nebula is where I release new exclusives and bonus content every month, and it's also where every episode of SFIA premieres early and completely ad-free. Right now, with my link or the QR code on the screen, you can get 50% off an annual plan, just $30 for the whole year, about $250 a month. Head to go.nebula.tv/Isaac Arthur and start watching today. Can we ever bridge the mathematical gap? Despite the dizzying possibilities for alien mathematics, there is still room for optimism. Even if alien minds differ profoundly from ours, the universe offers common reference points that any intelligence must contend with. We may not share symbols, intuitions, or logic, we do share the same physical laws, at least in this universe. A hydrogen atom emits light at specific wavelengths, gravity curves trajectories, a proton has a certain charge and mass, an electron has the opposite charge and a very different but specific mass. Rotating bodies develop angular momentum, waves interfere, information can't be stored, transmitted, and lost. Any civilization capable of building machines or radio telescopes must grapple with these constraints. They may describe them differently, but the phenomena themselves are the same. The ratio of proton to electron mass is the same, pi is the same, the number of times our planet rotates around the sun for every time it rotates around its own axis is the same. Probably, again, we might actually be in a subjective reality. Intelligence recognizes intelligence, and once it has, it will begin seeking to better understand it, even if it is just to wipe it out more efficiently. Where numbers may differ, patterns offer common ground. Ratios, cycles, periodicities, and symmetries appear in everything from orbital mechanics to molecular vibrations to musical harmonics. A species that sees with sonar, a species that perceives electromagnetic fields, and a species that swims through turbulent gas layers will all find these relationships woven into their experience. Information theory is another likely bridge. Regardless of biology or logic, every intelligence that builds communication systems must deal with noise, error correction, redundancy, and compression. Whether they describe entropy in our terms or theirs, entropy will still be there. Even if their bits are musical chords or chemical pulses rather than binary digits, they will discover limits on information storage and transmission. Computation too may form a shared territory. A species capable of technological civilization must eventually create systems to model, predict, or manipulate its environment. Whether through symbolic reasoning, geometric intuition, or emergent group computation, they will encounter constraints: finite memory, limited processing time, the need for algorithmic efficiency. The details may differ, but the challenges will not. There may be rare exceptions where they have an easier time to space or are naturally suited biologically for multi-century dormant periods, allowing low-tech space travel. But this is likely to be a rarity, not the norm, and thus probably not our first contact. Still, the path to understanding will be long. The first mathematical message we receive from aliens might not look like mathematics to us at all. It may appear chaotic or overly regular, too dense or too sparse. We may need years to realize which parts are structure, which are noise, which are constants, and which are variables. And that is assuming the aliens want to communicate in a way we can understand. They might assume their structure is obvious and fail to realize how alien it is. They might use their own logic without imagining other species could reason differently, or the message might be intended for minds very unlike our own. Something I've learned from homeschooling my own kids in math is that even to bright minds, seemingly obvious patterns can get missed even when staring at them for long periods. But if we are patient and curious and humble enough to recognize our own mathematical parochialism, we may slowly unravel their intent. We may find that behind the unfamiliar symbols lies a familiar truth. The universe is patterned, structured, and knowable, and though pathways are different, the destination may be shared. Mathematics might not be universal in form, but it may be universal in spirit. Every intelligence that gazes in the cosmos wonders how things fit together. Every species that builds tools must find ways to describe and predict its world. Every civilization that reaches for the stars seeks patterns that endure. The first alien mathematics we encounter may not teach us how to build new machines or solve unsolved theorems. Its greatest gift may be something deeper, a glimpse of how another mind, shaped by another world, finds meaning in the fabric of reality. For my part, I do think we will find common ground quickly by the same reasoning Sagan gives in Contact. Our physicists can talk to their physicists because both will assume the other wants to use relatively universal units like Planck lengths. I assume Contact, if it happens, is a multi-century game at a minimum, not showing up in a saucer on the White House lawn and marching down a boarding ramp to say, "Take me to your leader." If you show up in person that way, you only do it if you already decoded their language. When we speak of alien mathematics, we are speaking of alien minds. We are acknowledging that intelligence might arise in forms we can barely imagine, shaped by worlds unlike our own, guided by senses we do not possess. The aliens will, unsurprisingly, be rather alien, very different from us. So in many ways, the pursuit of alien mathematics is also a pursuit of unity. The universe is vast, but its patterns are shared. Somewhere out there, another civilization may be exploring those same patterns, asking their own versions of our questions. And if one day we exchange mathematics across the stars, the encounter will not be a meeting of equations, but a meeting of minds, different, extraordinary, and curious in their own ways. Until then, we continue the search, not merely for signals but for understanding, knowing that the next great discovery may not be a new star or a new planet, but a new way of seeing the universe through someone else's eyes.